right, before we begin, just a comment. This live stream is viewed both by my Orgo 1 and Orgo 2 students. So if you're kind of listening in the background and you hear something that's really kind of unfamiliar to what we're talking about, so if you're in Orgo 1, I start talking about alkadienes, or if you're in Orgo 2 and you wonder why I'm spending all this time on drawing line bond drawings, I'm probably not talking about something relevant to you. I will try to preface what I say so it's clear if I'm talking about Orgo 1 or Orgo 2, but yeah, do keep in mind that it's being serviced by both classes, so you're probably going to get a mix of what the other groups are saying. So I see that there's 2 of you watching right now. What questions do you have for me off the bat? Oh, actually there's no concurrent viewers right now. So I am going to comment on something I saw with my Orgo 2 students. And your discussion board gave you a series of alkenes and one alkane to look at. So you had 2-methylheptane, 1, 2, 3, 4, 5, 6, 7. And make sure I'm writing this down right. So the top 4 were the ones that you were asked to work with, and you were asked to name what the problem. Number 2 on the homework is hydrogen placement. So we'll get to your question next, Lauren. I just want to make sure I answer some concerns I'm having with Orgo 2 students. So for Orgo 2, I gave you guys 4 compounds, and I asked you what would be the product if you reacted each of these with a half equivalent of Cl2 and light. And there were a few points I was trying to get at with this discussion board. One, make sure that you can still kind of remember how to name alkenes, add that little bit about dienes in there, and so also to make sure that you're keeping up with the material in terms of looking at aliphatic hydrogens. So with all of these, with the exception of the alkane, you're going to get substitution near the double bond. Now for this one, you're going to follow the rules you learned when you worked with reactions. You're going to get the chlorine there. Here you've got 2 sites where you can get substitution. Here you've only got 1, and here you've only got 1. And this is going to lead you into part 2, which is the synthesis. It asks you how do you form 2-methyl-3-chloroheptane. And this compound here, which is this compound here. So what we're looking for is the most efficient route. Now, in principle, 2 of these can be used to make this compound, but one of them at best is going to have 50% yield because you're actually going to get a mixture of the 3 and the 5 chloromethane, or the 2 and CO2, 3, 4, 5. The 2,5 mixture of the chlorinated product. So there is really only one answer that will get you this insufficient yield. So take a look at the final product. Take a look at your starting alkenes and see which one's going to give you selective placement on this particular chlorine. Now, I've got a 251 student that's asked, can we go talk about number 10 on the homework? So let me bring up the homework really quick. Take your sweet time there, Internet. There we go. And under quizzes and assignments, almost there, Lauren. Oh my goodness, just show me the assignment. There we go. Let's get down to question 10. So again, the question was, is hydrogen placement a matter of following the octet rule? More or less, yes. So I'm going to switch the screen over so you can see at least what my version of this problem is. So the problem is asking you how many hydrogens are on around each atom indicated. So one, you're seeing the answer on my end. So this was the particular question it gave you. You see all the answers. So there are two ways we can approach this. One is to use the octet rule, which says that carbon has to have 8 electrons around this, and this translates into 4 bonds. So actually what we're going to do is we're going to exploit that. Typically carbon ends up with 4 bonds. So when you have your line bond drawing, carbon's going to have 4 bonds, oxygen's going to have 2 bonds, nitrogen's going to have 3 bonds, and for carbon, anything that is not drawn as a bond, unless we explicitly state it as a lone pair, is a missing hydrogen. So in the case of this atom here on the left with the phenyl ring, we have 1, 2, 3 bonds around carbon drawn. So the missing 4th bond is going to be hydrogen. When we look at this hydrogen with the OH group attached, we see 1, 2, 3, 4 bonds coming off that carbon, so there's no missing hydrogens. When it comes to this carbon here, the methylene, we have 1 bond, 2 bonds, so our missing 2 bonds that aren't drawn are going to be hydrogen. Now nitrogen gets 3 bonds, so anything that's not drawn would be a hydrogen, though typically with nitrogen and oxygen we do actually write the OHs to specify that they're there. Again, with this carbon here we see 2 bonds, so there's 2 hydrogens. For this we see 3 bonds, we need 4 bonds, so that 4th bond is going to be hydrogen. And for this carbon hanging off the end of this line, we only see 1 bond of that carbon, so the 3 missing bonds are going to be the hydrogen. So to answer your question, it is related to satisfying the octet rule. Carbon has to have electrons, and typically it's going to accomplish this by creating 4 bonds. Now, because there are so many hydrogens in the drawings, we typically just omit those, and we only write carbon-carbon bonds or carbon's bonds to other non-hydrogen atoms. Any missing bonds from that count of 4 are going to be hydrogens, unless we specify like a lone pair or a carbocation. In that case, we get rid of a hydrogen. So if we had something like this, so we had a plus on this carbon, we would kind of count that towards the bond count, or if we had a negative or lone pairs, we would count those two towards the bond count as well. So in terms of this drawing, this carbon has 3 bonds, so the missing bond's a hydrogen. This carbon has 2 bonds and the charge, which leaves it with 1 hydrogen. This carbon has 2 bonds and the charge, which leaves us with 1 hydrogen. This bond has 2 carbons with a lone pair, and that leaves us with 1 hydrogen. So hopefully that answered your question. Yes, so that extra bond is going to be the OH. And yeah, if there's any exceptions to these general patterns, that's why they're specified in line bond drawing. So something like a carbocation, we would put the positive on there to indicate that it's different than what you'd expect. So I got another question about the labs this week. It is virtual in the sense that we'll be working with a virtual assignment. The original plan was not to do the labs in person this week. We were told we had to do the labs in person this week. So yes, you are physically showing up, but for Orgo 1, there are no pre-labs this week. This is a paper lab. It's a recitation session. It's meant to give you more experience with doing the line bond drawings, working with the modeling kits. We're also going to do some virtual stuff where we're going to work with there's 2 pieces of software we're going to work with. Hopefully we can get the ACD Chem Draw on the laptop so you can get experience with that. That's very useful for doing your lab reports. And you'll also get experience with mold view, which will let you do three-dimensional structures and rotate them so you can actually kind of get a feel for this. And also to give you practice with the model kit. So it is technically a virtual lab in the sense that we're going to be working with a lot of software, but we are physically in person this week. I had hoped again to kind of not do this lab in person, but we were kind of told it is a hybrid lab. We can't keep doing these things online. Last week was okay because none of you had received safety training. This week we actually have to start doing the physical labs. And that'll be true either until the end of the semester or if the county goes back to phase 1. Yeah, you're welcome, Lauren. But yeah, I'll correct the announcements after I get done here today to reflect that. We're not doing them in person, but this was a decision that was made last week, but like Friday. Should probably correct those right now. I am glad to see the announcements went out. This was not true over the summer. You're welcome. Again, please feel free to email me any questions you have or ask questions during live streams. We are kind of having to be very adaptive with the labs, with the hybrids, because we are kind of we don't know from week to week if we're still going to have the labs. Sure. Give me just a minute to update this announcement. We'll go over Fischer Projections. And again, I do apologize for that miscommunication. Okay, so Fischer Projections. Let me get my modeling kit off the bench. So a Fischer projection is used for finding chirality more than anything else. It's a really good way of basically quickly identifying the chiral centers and identifying their RS configurations. So what I'm going to do is I'm going to bring up an example from the course website on that on those study packets as soon as I can download them. And just so this way everyone has a copy of the question I'm going to be answering. Now, the best way to do Fischer projections is to work with the modeling kit. So if you're trying to do this without a modeling kit, unless you're just very good at three-dimensional reasoning, I think you're going to struggle a lot. The best thing to do right now with Fischer projections, just because you're getting started with them, is to go ahead and get the modeling kit, build the model, and then rearrange the model to make it look like you would expect for a Fischer projection. All right. Almost got the problem up. So for the Fischer projections, I'm going to work on the ones that are in the study packets just so that everyone has access to them. I know with the McGraw-Hill homework it can sometimes change. So the ones we're going to work on, this 2s, 3s, 3-bromo, 2-butanol, and this 2r, 3s, 3-bromo, 2-butanol. Now again, you're not responsible for knowing how to name the bromo-butanol. For Orgo 1, you're just required to be able to, you're just expected right now to be able to figure out the chirality on the second and third carbons. So I'm going to go ahead and draw these up on the board behind me. So the 2s, 3s, and the other one I think is, yeah, flip, 2r, 3s. So to determine the Fischer projection, first thing you want to do is actually build the molecule with your own modeling kits. So in this case, I'm going to represent the oxygen with the red, and I'm going to represent the bromine. I'm trying to find a color other than white. Let's go with blue. So I'm going to do the bromine in blue. So to build this molecule, I've got my carbon backbone, so I've got 4 carbons. I've got the bromine going back and the oxygen going back. So this would be the structure of this line bond drawing. Now the Fischer projection itself is what would happen is if we took the carbon backbone and we made it into a loop. So with 4 carbons, it's going to be a C shape. If it was 5 carbons, it'd be a loop. If it were 6, it would end up being a coil, and as we got further and further, we would see it coiling more and more on itself. So your Fischer projection, you draw it by drawing a vertical line, and that's going to represent your carbon backbone. We're going to write out what's at the end of each end of the carbon backbones. In this case, we've got a CH3 and a CH3. For every carbon along the backbone, we're going to have a horizontal slash. Correct, the red is oxygen, and I'm just going to go blue with bromine because it's got the best color contrast. I find the white's pretty hard to see against this whiteboard. So it doesn't matter which end of the chain you start with. In fact, my keys are coded so this way you can do either one. I prefer to put the left at the top and the right at the bottom. If you choose to invert that, you're going to see that this is just, you can get the same thing just by rotating this 180 degrees. So let's start by going to the next carbon that has the oxygen. So this is going to be the OH carbon, and this is going to be the bromine carbon. Now, to draw the Fischer projection, take your top carbon, and you're going to move to the next carbon, and you're going to look between the 2 atoms that are not the carbon. So here we've got an oxygen on the the left side and a hydrogen on the right. So we'd have OH and H. And the way that we would draw this stereoscopically is we've got the carbon here, hydrogen coming out, the OH coming out, our CH3 going back, and the rest of our chain going back into the board. So what you're seeing when you do the Fischer projection is you're looking between the bonds of the two atoms that are not, you're looking between the bonds of the two atoms that are not the backbone. Is the CH3 always at the end? Typically, I mean, if we had something like an OH down here, we would have CH2OH. So traditionally our bonds our Fischer projections terminate with carbons. They don't have to. We could also draw this, if we had an OH down here, as this. It's more a matter of what you want to emphasize. Traditionally, they're terminated with CH3 groups or with our CH groups because we're using this to find chirality, and your N groups, something like a CH3 group doesn't have chirality. So this is more for tweezing out the chirality. These ends, unless they're chiral, which typically they're not, we're just going to write them as groups. So I'm going to keep moving along. So that's this carbon. Now we're going to move to the next one. The next one we're going to look, and you've got the bromine on the right side and the hydrogen on the left. So this is going to be H, and that's going to be R. And that would be the view you get if you take this alcohol-containing carbon and you rotate it so you're back. It's really hard to do. So you rotate to the next carbon. So this would be the Fischer projection of this compound. Now, the power of the Fischer projection is that this was the 2R, 3S. To switch between R and S, we just flip these two groups. So based on how Fischer projections work, the 2R, 3S should look like this when we get done drawing it. So what I'm going to do is I'm going to rebuild this molecule and see if it matches up. So again, build your carbon backbone. So we've got that zigzag pattern. Our bromine, the blue, goes back. And in this case, our OH group comes out of the board. And we get a structure that looks like this. So you can kind of see the OH here, and then the OH in the background. We've got the bromine there, and we've got the bromine here. To do the Fischer projection, we're going to rotate all the carbon bonds so it forms a coil of carbons for the backbone. If we start with the CH3 group that's here, CH3 group that's here, and then we rotate so we're looking between the bonds of the non-backbone atoms. We've got the red on the right, the OH group on the right, the hydrogen on the left, and that's what we have here. So the OH group here is on the right, hydrogen's on the left. If we keep turning the coil, we get bromine on the right side, hydrogen on the left side, and that's what we have here and here. Now, we can also work to a much more complicated example, which I'm pretty sure I have. Oh yeah. So before I go on, are you comfortable with the two simple examples I just did? So when I say looking between the two bonds, we've got this carbon backbone, the zigzag. So what we want to look at is this point here in the Fischer projection, this cross. That cross represents a backbone carbon. So the intersection of these two lines is a backbone carbon. And when we're looking at a Fischer projection, we're looking at it as we're looking along the backbone. So the Fischer projection is drawn as if you're moving down the backbone. The horizontal lines here represent the two atoms that are also bound to the carbon. So when we say we're looking between the bonds, what we mean is that if we're looking along the backbone is kind of straddles between the two other atoms that are bound to the carbon. So the way that Fischer projection is written is that you're looking right there between, in this case, the bromine bond and the hydrogen bond, or if you move to the alcohol, you'd be looking between, this is really hard to do. You're looking between the alcohol and the hydrogen bond. So we're looking basically, carbons are tetrahedral. We're looking at between the two bonds of the other two atoms that are bound to the carbon. That wasn't a good way to explain it. Just a quick question from our Orgo 2 student. Just got to ask for Kim 252 question from the discussion board. Is it correct that the reaction of 6-methyl-1,3-heptadiene with a half equivalent of Cl2 light would form a chloronium ion? I am not familiar with the chloronium ion. Typically we call them radicals. So you would form the chloride radical, Cl. Answer this question really quick. You would form two equivalents. You would form the Cl radical. And that radical would abstract the hydrogen to give you the diene radical. And then that diene radical would react with a further chlorine radical to give you the Cl bond. So when I talk about like what goes on, just more qualitative to describe that, you would generate a chlorine radical that would create an diene radical, and then the diene radical would react with the other chlorine radical to turn back and give you the chlorine final product. Now, Ksenia, to get back to your question, so are you comfortable so far with just the simple 4-carbon molecule? And we are going to work with the modeling kits a lot more in the lab and do a lot more of the Fischer projections one-on-one. So the homework and the packets are not the only practice you're going to get with this. You're welcome, Nicole. All right, so let's work with a real, so in this case, Ksenia, let's work with a much harder one. So there's one in the packet. And the idea with these super hard ones is to show you it's more just a process than anything else. So if you understand the process, a lot of these are just kind of the exact same problems over and over and over again. So we got 1, 2, that. BR and BR. So I've got this gigantic monstrosity of a molecule, and I've got an OH and 2 bromines hanging off of it. So to do the Fischer projection, you're just going to draw the straight line. We got a CH3 group here, CH3 group here. They lack chirality, so we might as well just write them as CH3. And we've got 1, 2, 3, 4 additional carbon atoms in the backbone. So let's build this structure with the modeling kit. So again, my blues are going to be my bromines, and my red is going to be the OH group. So I've got an OH group going back, bromine group going back, and bromine group going back. Now, there are actually ways, I will give you the full disclosure, there are some people that talk about how you can figure these out without ever having to build a modeling kit. You will always have access to modeling kits, so I say keep it simple. Anyway, this is our molecule when we get done building it. So we've got the zigzag chain, and we've got the OH group, the bromine, and the bromine going back. Now, to draw the Fischer projection, what we want to do is we want to take our long molecule and we want to turn it, rotate the carbon-carbon bonds so that we end up forming a coil. So we've got the backbone atoms all in a loop. We'll start with the methyl group closest to the OH. So we've got this methyl group, and we're going to rotate it up, so this way that we've got the backbone going up and down, so this carbon, this carbon, this carbon, the backbone. And when we look between the bonds, we've got the OH on the left side, and we've got the H on the right. So we'll draw that in. Now, to get to the next carbon, we rotate. And looking between the bonds, we've got the OH, we've got the bromine on the right and the H on the left. Rotate to the next atom, and we've got two hydrogens. So we've got an H and an H. And then rotate to the next atom. We've got our 3 carbons in a row for the backbone, 1, 2, 3. Looking between the bond, we've got the bromine on the right side, and we've got the hydrogen on the left side. And then we finally terminate with the methyl group. So the reason I had to curve it into a circle is that if we look at the Fischer projection, each atom along the backbone goes back relative to each other. So if we were to look at the carbons above and below, they would be pointing into the board, whereas these two atoms going horizontal point out. So the only way to get that to happen, or the easiest way to get that to happen with our modeling kit, is to form a loop. So we always want the two adjacent carbons in the backbone to be backwards when we're looking at the Fischer projection, and we want the horizontal atoms to be pointing out. So if you were to do a zigzag, like the molecule starts as, so we use the staggered conformation. There is a way to do this, but basically if we try to look down the chain, these are correctly oriented, but for the next one, they're pointed the wrong way. They're actually pointed towards you, and we'd really need them pointed the other way. Now again, you can do it this way, where you go down and you just keep rotating the molecule back and forth to see how you would project into the Fischer projection. In terms of practicality though, it's just a lot easier to form this loop. And then with the loop, you've always got the next carbons in the backbone always oriented in the correct direction. They're always pointing, from your perspective, looking at my webcam, you're pointing back into the board, and the atoms that are parallel are pointing out. And if we were to go from the Fischer projection back to the stereo drawing, we would do the same thing, is that we would create a loop, and then we would just move along the loop and put the atoms the way we see them. So if I were to withdraw the OH groups and the bromines, I know it's a 5-carbon chain. 1, 2, 3, 4, 5, 6 carbon chain, sorry. I've got my methyl group, and the next carbon in the chain's got the OH group on the left side. If we go to the next carbon, we've got the bromine on the right side. The next carbon is 2 hydrogens. And then once again, we got the bromine on the right side. And now we can just rebend it into that zigzag shape and get back out the geometry we want. So I just got to ask what lab questions or assignments are due this week, and are we supposed to have the molecular modeling labs introductions in our notebook? So the molecular modeling, no. You are going to do a worksheet and turn that in via the course website, but it does not go into your lab notebook. In terms of what's due this week, you need to upload the worksheet for the molecular modeling lab, but that's not due until next week when you go to lab. So in terms of lab, there's really nothing that's really due, but you do have an assignment that you're working on that is due next week. But this week is for Orgo 1, it's the in-person for going over Lewis structures, building modeling kits, and introducing you to the software that you're going to be working with this week. Hopefully we can get the ACD ChemDraw uploaded to the laptops, as well as MoleView, and those will give you two different ways of drawing the molecules, both for your cells as well as for any lab reports. But this week, this is really the week where we start labs. And we're starting on a paper lab, so there's no pre-lab. There's only the worksheet that's technically due as a post-lab, but nothing goes into your lab notebook. Other questions? So again, just as a reminder, we do have physical labs this week. I just sent out the corrected discussion board for Organic 1. It did say virtual. That was the original plan. Last week that got changed the last minute. I just didn't catch it in the announcement. But we are definitely doing physical labs this week. It is molecular modeling. Make sure you bring your modeling kits with you. I'm sure the Orgo 2 students will probably chat at some point saying that yes, these organic modeling kits are incredibly useful. It is very hard to do the spatial reasoning by yourself, so these modeling kits kind of take a lot of the strain off of you. We're also going to be working with 2 pieces of software. One is ACD ChemDraw. It is a freeware software for drawing organic molecules. It's a little clunky, but it is a free program. It will clean structures for you, and best of all, it will create nice figures for any lab reports or anything that you're submitting for your lab assignments. We're also going to be working with MoldView. MoldView is a freeware software put out by the National Institutes of Science and Technology. It lets you do 3-dimensional drawings. It lets you do electrostatic potential maps. It does a lot of things. The biggest issue is that unlike ACD ChemDraw, which lets you create images for Word documents, best you can do are screenshots. But again, it's meant to provide you with an additional tool for not just drawing molecules, but in this case, manipulating them in three-dimensional space and seeing what they look like. Excuse me. Now, as hopefully you all saw this week, you're going to get an announcement every Sunday, first thing, that's telling you what's due that week. It'll also have links to all the live streams. If there is an exam, it will provide you with a link to the exam itself. Now, if you don't see the announcement, I'm kind of curious. I think there is a bug in Blackboard that if I send out an announcement with a link that isn't available yet, it may wait to send out the announcement. Go check the course website if you don't get it. I'm not 100% sure that's what's really going on. I just think occasionally Blackboard just doesn't send out my announcements. But again, if you have questions about what to do that week, it's available there. There's also the My Grades ribbon, or My Grades course menu, that will show you what assignments are due, when they're due throughout the entire semester. There are a few that are not up there yet because they are intentionally hidden from you, so you don't try to get a jump start on those assignments. But again, most of the due dates are going to be available for you on the course website under My Grades. You'll get announcements, and this is how we're going to do most of our communication. But again, you have these live streams as well. So if you have questions that you want to ask, email them to me in advance. If you're not going to be able to make it to the next live stream, I will try to answer email questions at the front. And because Orgo 1 and Orgo 2, both of y'all are sharing the same live streams, I will try to preface beforehand whether or not this is Chem 251 or Chem 252. You are also free to discuss amongst yourselves in the chat board if you've got comments or questions. Like, I'm not going to object if you answer someone else's question. I mean, I'll correct you if you're incorrect, but again, like, if you know the answer and you want to answer it, go for it. Like, students learn better learning from each other than y'all are going to learn. And studies have shown this. Y'all learn better talking to each other than you learn talking to me. So are there any other questions out there? We still got another 16 minutes left. So in terms of how you're studying, if the videos are more useful to you than PowerPoints, use the videos. If the PowerPoint's more useful than videos, use that. If the book's more useful, use that. I'm not going to tell you how to study. People just have different learning styles. I personally do better reading a book and taking notes in a book. I really can't follow PowerPoints. And I like videos, but I definitely need to write things down. In terms of pacing yourself, that's kind of where the announcements and the discussion boards are coming from, is to say, okay, you should be about here in the material. The big thing is the homework. So you should be able to do roughly a third of the homework each week. So in this case, for 251, you've got 66 questions. You should be able to do roughly the first 22 this week. Next week, I'm sorry, when is your exam? I think your exam's in 4 weeks, actually. However many weeks you have to do that exam between now and the exam, that's where you need to be divvying the material up. So I think the exam's in 5 weeks. You've got 66 questions. It's roughly 12 questions per week. So just kind of see where you are in terms of those questions. All these materials are kind of provided to address all the different learning styles. So again, some people really don't do well with PowerPoint slides, or they don't do well with the books. The videos that they're provided to provide you with a means of access. Same thing's true. Yes, the homework is definitely in roughly chronological order. That's why I try to set it up the way I did. So the questions come from the book, but I organize the homework assignment itself. And you're going to see it starts out with doing line bond drawings, and then it's going to start switching into chirality, and then it's going to start switching into analysis and characterization. Analysis and characterization we're going to cover last for 251 prior to the test. It is a harder concept to understand, but if you don't understand how to read a line bond drawing, you're kind of dead in the water with doing that type of analysis. So yes, the homework is for the rest of the semester, both Orgo 1 and Orgo 2. It's roughly in the chronological order in which you'll be learning it. And I say roughly because the book is a little weird in some of the questions it asks. So it may be a little bit here or there, but for the most part, it's in the right order. So when we get to alkanes, like the first thing you're going to cover for the homework is naming. That's where we're going to be in the material, and then we start going into reactions. Yeah, you're very welcome. As my rate my professor reviews have probably told you, if I tend to be pretty straightforward and the tests tend to be easier than the homework materials themselves, I think that's more fair. The homework is just there as a final assessment to say, okay, did you actually understand it? But I don't see a reason to give you gotcha questions on the homework, and I don't see a reason to be coy. I don't see a reason to give you a gotcha question on the exams. I don't see a reason to be coy about what's going to be on the exam. I try to be very straightforward about what the expectations are. All right, so I'll give it about 5 more minutes. If no one's got any more questions, then we'll just sign off for the day. right. If there are any other questions, then we'll go ahead and sign out for the day. And yeah, I will see half of you tomorrow. Thanks for showing up.